Okay, so now we discuss shear center and shear flow. Now imagine we have got the I section, cross section, and which is cantilevered of a surface. So in other words, we have got a cantilever beam. Okay, and we apply load over here. Okay, so we have got a cantilever beam which is subject to some load. Okay, or let me draw it over here. Cantilever load, and this load is applied at this. So it is fixed over here, and we have got I cross section. Load is applied in this direction. Now, as I told you, that we can assume that the whole structure is divided or discretized into small boxes. Okay, and what we are trying to find out is how the shear is flowing. Okay, in your welds. Shear will always flow in the welds and flanges. Okay, and as I told you, this is because of the unbalanced moments as we discussed. So we have to find out how the shear is flowing. So assume that I take a piece like this. Piece like this. Okay, so these are small boxes. I am assuming that I have divided this into infinite number of boxes, but what I am interested in is finding out how the shear is flowing in here. Okay, what is the direction of shear? Now, if you find one unbalanced force, you can equilibrate the whole box and you can find out the other shear forces. Okay, so how do we do that? Because it's a cantilever beam, so the shear force diagram, the bending moment diagram of the cantilever is like this, isn't it? We discussed it. And so in other words, the moment at this point will be smaller than the moment at this point. Okay, so at this point it will be bigger than the moment at this point. Do you understand why? Because as I've shown you that the moment over here is bigger than over there. So wherever, if you are closest to the load, okay, the moment is smaller. If you are closest to the support, the moment is bigger. So that tells me, and this end will be in tension. Okay, so this is just like I'm putting it like this. This one is in tension, and this one is in compression. So what will happen? Should I put my force? So this is in tension, this is in compression. So compression will be So the question is, how should I put my tension force? That is the main question. What would be the direction of the tension force in here? Now, because the load closest to the moment closest to the load is bigger than the moment closest to the support. So that tells me that I have to apply load in this direction. In this direction. Okay, and similarly I have to apply load in this direction. Why? Because in order to balance out my loads, the load over here is bigger and the load over here is smaller. So I have to apply my load in this direction in order to make it in equilibrium. Are you getting what I'm applying load in this direction? As I have told you that moment over here is smaller. So if the moment over here is smaller, the compression and tension forces are smaller. So I have to increase the compression and tension force in order to make it equal to this one. And that's why I apply my load in this direction. Now if I apply my load, so this is just like imagine I've got a box like this is a box, okay? I've got a force applied in this direction, which is, so if I apply load in this direction, I have to apply an equal load and equal and opposite load in this direction. So if this is applied, this one must be in opposite direction, and they cause counterclockwise movement, so I have to apply a clockwise load in this direction and in this direction. So I get force in this direction, in this flange. I'm just trying to make this box equilibrate this box. This force I got, why? Because of the difference in the loads. And once I get this force, then I know that at the other end of the box it would be equal and opposite, so I applied equal and opposite force. But they are causing a couple in counterclockwise direction, so to counteract that, I have to apply an equal couple in the opposite direction. So which gives me this. So this gives me this force. And similarly, look at this one. This one is the same.
So the couple arrows same. These are the MOSII parameters.
Sorry, thank you. Yes, this is, thank you. Yeah, this is equal and opposite. Yes, this is like this, so this has to be yes. This has to be counteracted. Okay, so this is in this direction. Yes. So similarly, in this case, I've got force in this direction. I will apply force in that direction and a couple in this direction. Okay? So So my shear flow will start from here then it will go like this. You can do the same thing over here. In here, I applied these two. In here, I have to apply this will be in the opposite direction, which is this one. Why? Because this is in compression. Okay, so the compression one, so why have I applied over here in this direction? Because the bottom flange is in compression, and the compression force which is closest to this one, to the root, that is okay. Now the compression force which is closest to the root, that which one is bigger? The one which is towards the which one is bigger? The one which is towards the load, that compression force is bigger. Which is in this direction, towards the support. That compression force is bigger. Agree? So if that compression force is bigger, then which direction should I apply my load?
Away from the support.
So again, so in other words, what I am saying is that I've got we have tension at the top and compression at the bottom. Okay, so it's the same section which is say 1 and 2, and this 1 and 2 have taken over here. Now this one, so 1 is closer to the load, so this one is less. Okay, this one is less, this one is more. Okay, so if this one is less, then we have to apply load in this direction. Okay, and we have applied load, for example, in this direction. Okay, we have applied the load in this direction, and now come over here. Over here, what do we have? This is at the bottom. In the bottom one, we have both in compression. The compression one, this too, it is bigger than the one. So we have to apply force in this direction. So I have to apply force in here like this. Okay, to compensate for this one. Okay, and so once I apply load in this direction, I will go like this, and then like this. Okay, so this shear flow, in other words, comes like this, and do you understand my point? This shear flow starts from here, and then it goes like this, and it goes. Any question about this? Any question? What I am saying is, how have the main crux of our discussion is how do we get this flow? This flow you can get by equilibrating this box. As I said, you divide the whole structure, the whole component into boxes. Okay, and you will normally get the unbalanced longitudinal shear, and then based on unbalanced longitudinal shear, you equilibrate your box. So it's up to you how you want to go about it. So for example, I've got this box. Okay, this box, as I told you, has got compression and tension. The section 2 is closer to the support, so it is bigger. Okay, its magnitude is bigger. The magnitude of these forces is bigger than section 1. So you must apply a force in one direction so that both of them become equal, and that unbalanced force is applied over here. If you apply that in this direction, this unbalanced, so the shear flow will become like this. It will all become opposite, but it doesn't matter. You want to take it from top to bottom or bottom to top. It doesn't matter. The main thing is that you have to equilibrate this box. So I have told you, remember 3 steps. Okay, the first step is you draw the bending moment diagram. See where your moments are changing. Okay, that will tell you. So once you find out that, the second step is you find out your unbalanced force. So the unbalanced force you find out, put it in that box. Okay, the unbalanced force. Then the third step is you equilibrate that, and you find out your flow on the cross section. So that's how you determine the shear flow in the region. Now, as we said that tau is equal to VQ by IP or IT. You can also multiply this curve with V and you get VQ over I. So in other words, you can normalize, this tau is actually normalized based on the width B. So you can remove that dependence on width B. So this is called Q, which is a shear flow. So in other words, if you are going like this, you are trying to find out your shear, your width B is this one. When you come over here, for this, the width B is this one. And then it reduces to this one. Okay? And then over here again, it is this one. This is your width B. Okay? The width B is always perpendicular to your force. Please notice that. You have got shear flow in this direction, the width B is the thickness of the flange. When it comes over here, the width B from the width of the flange, it reduces to the thickness of the web. And then again when it comes over here, the width B becomes thickness of the flange. Okay, so that width B dependence can be removed by multiplying both, by taking this B over there, and then you will have simply BQ over I. So you can find out the magnitude of all these shear by multiplying B, by finding out B. B is the shear on this cross section. So that is the maximum shear which you will get from the shear force diagram. I is the moment of inertia of this cross section. Q is something which you have to adjust to find out your shear cross section. And so if you are trying to find out your shear of the flange, okay, you take B, you take Q as thickness of the flange times the length of the flange, and Y bar would be the centroid of this to the neutral axis, as we did in the previous example. And similarly, if you are trying to find out for the web, it will be this, the area, the shear contribution of the flange plus this area and times Y bar. Okay, so that thing you have to understand. Now, the problem comes, now this is a symmetrical section, and you can see that in symmetrical section you have got very smooth moving of these forces, okay, and the equilibrium is satisfied. But what happens if you don't have a symmetrical section? In other words, if you have a channel section like this, imagine I've got a channel section which is against, like which is subjected to, which is in the form of cantilever, okay, a cantilever of channel section. So what happens is that you will have again okay, you will have a shear flow which looks like this one. If you want to find out the shear, the total shear in the flange, you just take top, multiply that with the area of the flange, you get the total shear force in the flange. If you want to find out the shear in the web, take top and multiply that with the area of the web. And similarly for the lower flange. Now you can see that, now look at this symmetrical cross section. You have got this shear flow, so the resultant of all these forces will give you one force which is in this direction. Agreed? Another resultant of this will give you one force which is in this direction. Okay? Another will give you in this direction. Another one will give you in this direction. Okay? Now, this couple and this couple. Look at this one. This and these two are couples, isn't it? They are causing a moment in this direction, and this one is causing movement in this direction. Yes? So, they are in equilibrium and they will cancel out. So, this section is symmetrical. And summation of Fy, this one is equal to this one. So, your Fy is equal to 0 is also satisfied. Okay, your Fy is equal to 0 is always also satisfied, summation of Fy. So it is the web which is taking your shear force, which is this one. So what I'm saying is that, as I told you, that you can have shear flow in this direction or shear flow in the opposite direction, which is like this. So I can also write it my shear flow can also be like this. My shear flow can also look like this. How can I get this one? By assuming these forces. If I take, imagine, my resultant force I take over here, so I will get a force over there, and okay, I can do that also. Can't I? Can I do that? Why do I say I can do that? Because I've taken my shear force difference in this. This is actually dependent on whether I apply a load in this direction or apply a load in the opposite direction. Shear flow can be in any direction based on the load which I have applied. Okay, so I can have a shear flow in this direction, shear flow in that direction also. Now I'm saying that, you see, all the equilibrium conditions are satisfied. What are the equilibrium conditions? Summation of forces So the equilibrium condition are summation of forces in the x direction equal to 0, summation of forces in the y direction equal to 0, summation of forces in the z direction equal to 0. Summation of moment in the x direction equal to 0, summation of moment in y equal to 0, and summation of moment in z equal to 0. And you see, summation of fx is in this direction, so we have got no forces in this direction, that's satisfied automatically. Summation of fy is equal to 0. Fy is, you have got force in this direction and your shear flow is in this direction. Okay, so this force which is over here, that must be equal to this one, the applied vertical force. So summation of Fy must be equal to 0. Okay. Then summation of Fz, there is no force in the z direction, so that is 0 by default. Agreed? Okay. Summation of moment about x-axis is equal to 0. So in other words, summation of moment, so that is actually the flexure moment. You get, this one is the flexure one, and from this you get stress is equal to Ny over I. That condition you get from here. Okay, so that is automatically embedded in this. Summation of moment about y-axis must be equal to 0. So there is, the load is applied on the y-axis, so there is no force which is causing imbalance in the y direction, so that is also equal to 0. And summation of moment in the z direction, look, this load is, so in the z direction you have got these flange forces, isn't it? This force and this force. So I will have a moment in this direction and moment in this direction. These both moments, this flange force and this flange force, they are causing moment, isn't it? This is equal and this is equal. Agreed? They are causing moment, and this one is causing, this one and this one are causing opposite moment, so they are 0. So in the symmetrical cross section, all of these are fully satisfied. Now look at this one. what happens? I've taken only half of the I section. So if I remove, in other words, this flange and this flange, what will happen? What will happen to these equilibrium conditions? You will have movement in this direction. Why? Because you have got force in this direction and you have got force in this direction, equal. These are causing couple. In I section, they were equal and opposite forces which were contracting this couple. In the channel section, they are now contracted. Why? Because this couple will tend to rotate the cross section. Do you understand my point? So, what we have to do is, we have to so if you have the same load applied over here at the centroid, at the neutral axis, you will have this rotating. So you don't apply the load at the neutral axis, you have to apply the load at a particular distance from this y axis, okay, to have a contracting couple. And that distance, so in other words, this load must not be applied over here. You have to apply it at a distance from this E, and that distance is called shear center. If you don't apply this load at the shear center, okay, what will happen? Your section will twist. So in other words, these two forces, they will try to twist this. Okay, so this force, imagine that is your H1 and this one is your H2. These two forces will tend to twist this. Okay, move it in this direction. You have to apply your external load at some offset from the neutral axis in order to take that load. And that is called your shear center. So I suggest you look into the shear center section. Okay, and then we can have a discussion tomorrow. Okay.